Good morning, chemistry students. Here are your Chapter 9, Day 2 notes. So today we're going to talk about how to start some stoichiometric calculations. So again, you should have your periodic table with your helper sheet out. You should have your chemistry toolkit with those 5 tools, those 5 conversion factors out and ready to go. You should have a calculator out and ready to go. So today you're going to add a tool to your toolkit that's going to allow you to do all of these stoichiometric calculations. So this section is titled Chemical Calculations. And we're going to start by talking about a mole calculation. And again, keep in mind that we need to have our balanced chemical equation to do any of these calculations, because our balanced chemical equation provides lots of information. Remember that we can interpret our balanced chemical equation in terms of particles. We can interpret our balanced chemical equation in terms of moles. We can interpret our balanced chemical equation in terms of mass or weight. We can interpret our balanced chemical equation in terms of volume. So our balanced chemical equation is essential for all calculations involving reactants and products. So again, it's kind of one of the spots where your textbook or where I will try to trip you up, that it won't provide a balanced chemical equation. And so the first thing that you'll always have to do when you're completing a stoichiometric calculation is you will have to write a balanced chemical equation if one is not provided for you. The reason that this balanced chemical equation is so important or so essential is because if you know the number of moles of one substance, the balanced chemical equation allows you to determine, and realistically you're going to determine it by calculating the number of moles of all the other substances in the chemical reaction. So again, it's going to kind of be based a little bit on what we did the other day when we looked at our balanced chemical equation and we interpreted it in terms of moles. Remember, the coefficients in our balanced chemical equations tell us the relative numbers of moles of all of our substances. This allows for a new conversion factor. Again, the one that in a couple minutes you're going to add to your chemistry toolkit, called a mole ratio. And a mole ratio is important because you must use a mole ratio because, I put ration instead of ratio, because it's the only way to convert from one substance to another substance. So pretty much all of these stoichiometric calculations you're going to do, you're going to go from one substance in your chemical reaction to a different substance in your chemical reaction. Anytime you're asked to do that, the only way to do that is to use your mole ratio. So here's the tool for your toolkit, and we'll talk about kind of what this means in just a moment. Your tool looks like this. It's some number of moles of substance A over some number of moles of substance B. And again, the power of this is that I can flip it depending upon where I need my units and substances to be. The number here comes from the coefficients on your balanced chemical equation. Now, what is important here is you must include, you must include the substances formula, because otherwise you just end up with mole and it can get confusing. So this is our no tool. This tool is called a mole ratio. Okay, and it's some moles of A over some moles of B, where A and B are just different substances. The numbers in our mole ratio come from our coefficients in our balanced chemical equation. So we're going to take a look at an example. Oops. Well, we need to get another example in here. Let me see. All right. I'm going to just kind of put it in a different color here. We'll make it green. So if we have the equation, nitrogen reacting with hydrogen to produce ammonia, and we've used this equation already, so that's why we're not going to bother with balancing it right now. The mole ratios for this are, we can do quite a few of them, but there are definitely three that you could flip. 1 mole of nitrogen to 3 moles of hydrogen. And again, the number in front of moles of nitrogen came from the coefficient on nitrogen. The number in front of moles of hydrogen came from the coefficient. So that's one that I could flip. I can also do nitrogen and ammonia. So I can have 1 mole of nitrogen to 2 moles of ammonia. And again, the 2 comes from the coefficient in front of ammonia. And lastly, I can have hydrogen and ammonia. So I can have 3 moles of hydrogen to 2 moles of ammonia. Again, I have to have my units there because otherwise it's just moles and moles. So we are going to use this equation of nitrogen and hydrogen forming ammonia to do this problem. So again, I'm going to put my equation here. Actually, I'll go ahead and put it underneath. So we had nitrogen reacting with hydrogen to produce ammonia. Now, one of the things that I like to do when I do these problems is I like to summarize the information underneath the problem because most of them are going to be story problems. So it's asking how many moles of hydrogen, so that's my unknown, so I'm just going to do a question mark and I want it in moles, are needed to react with 3.8 moles of nitrogen when forming ammonia. So this problem's asking me to start with the 3.8 moles of nitrogen and figure out how many moles of hydrogen that is. So again, as with all dimensional analysis problems, I start with my given. Since moles of nitrogen, remember I could write this over 1, but I just don't. So since moles of nitrogen is in the numerator, I have to have moles of nitrogen in the denominator. And my only way to change from one substance to another is a mole ratio. So this is going to be that new conversion factor called the mole ratio. And in this problem, I'm asking about moles of hydrogen. So moles of hydrogen are going to go on the top in the numerator. So moles of nitrogen have crossed out. I'm left with moles of hydrogen, which is what I want. Now, where do I get my numbers from for this mole ratio? Those are the coefficients. So on hydrogen, my coefficient is 3, so I put a 3 in front of moles of hydrogen. On nitrogen, my coefficient is a 1, so I put a 1 in front of moles of nitrogen. Now remember, when we're doing dimensional analysis and factor label method problems, again, we multiply by numbers that are in the numerator or on the top, and we divide by numbers that are on the bottom. So hopefully we don't have to divide by 1 because you all know that you wouldn't have to do that. So 3.8 times 3 gives me, my calculator gives me 11.4, but you've learned about significant figures, so I need to pay attention to significant figures. This only has 2 significant figures. This is a definition, so it has unlimited sig figs. So my answer needs to have 2 significant figures. So 11.4 with 2 significant figures is just 11 moles of hydrogen. Again, this is exactly what problems should look like. You don't have to write what I put in blue there. You don't have to keep track of the significant figures. But everything else you see here should be on your paper. Again, you don't necessarily need to write that this is a mole ratio, but you need to show this work exactly like this. If you do it any other way, I'm going to count it wrong. If you don't show me all of this work, I will mark it wrong. So this tool, this mole ratio, needs to get added to your toolkit. So take a moment right now, pause the video if necessary, find your chemistry toolkit and get it added to your toolkit, please. So now that we have our new tool, our mole ratio that allows us to go from one substance to another, we're going to talk about mass calculations. Probably more than 80% of the calculations you're going to do in Chapter 9 in stoichiometry are going to be mass calculations. The reason for this is because there is no mole balance. Okay? So because there's no way to just put a substance on a balance and have it tell you how many moles there is, instead you must measure the mass, normally in grams. And because of that, that's going to require you to use multiple conversion factors to solve these problems. And I don't like you to just use one at a time. I want you to string all your conversion factors together and then do all of your math. So, the best way to kind of see this is to do one. Again, though, you need to have that chemistry toolkit in front of you, right? Because on your toolkit right now, you have 6 conversion factors now, right? You have 6.022 times 10 to the 23rd atoms to 1 mole of element. You have 6.022 times 10 to the 23rd formula units to 1 mole of ionic compound. And you have 6.022 times 10 to the 23rd molecules over 1 mole of molecular compound. You have the molar mass, right? We kind of call all 3 of these the Avogadro's number ones. You have the molar mass conversion factor, which has some number of grams of substance over 1 mole of that same substance. And you have the molar volume conversion factor, which has 22.4 liters of gas over 1 mole of gas. And that one, to use it, you're supposed to be at STP, at standard temperature and pressure. And now, today, you just added some number of moles of A over some number of moles of B, which is your mole ratio. Now remember, this number comes from adding up the molar masses, or the masses of your elements on the periodic table. Remember, these numbers come from the coefficients in your balanced equation. So you should have a tool that looks like this, a toolkit. And again, it should be on an index card, and it should be sitting out with you right now as you're taking notes, along with your periodic table and a calculator. So our first problem we're going to do is iron 3 oxide, also known as rust, is produced when iron reacts with oxygen. How many grams of rust are produced when 12 grams of iron rusts? Again, first thing we need for all stoichiometric calculations is a balanced chemical equation. And there isn't one here. So you have to write one. So again, pause the video right now and see if you can write a balanced chemical equation for this. So, again, I'm going to assume that you've gotten pretty good at writing balanced chemical equations. If you still need to do a word equation first, that's fine, but I'm going to discontinue doing a word equation first. Okay, so iron 3 oxide is produced, so that is a product. Okay, that's an ionic compound, so my symbol for iron is Fe, has a charge of +3. Oxide is O, charge of -2, so I'm going to write it as Fe2O3. Is produced when iron, so Fe, reacts with oxygen, which is O2. Now, I need to balance it. I have 1 iron, so I need a coefficient of 2. I have 2 oxygens, and I have 3, so I'm going to make them both 6. So I need a coefficient of 3, and I need a coefficient of 2, which means I need to fix this, right? And I need to change it from being a 2 to being a 4. So 4 irons, 2 times 2 is 4 irons. 3 times 2 is 6 oxygens. 2 times 3 is 6 oxygens, so it is balanced. Now, again, I like to summarize underneath my balanced equation what the story problem is asking me to do. It wants to know how many grams of rust, which is this, are produced when 12 grams of iron reacts. So this problem is asking me to take 12 grams of iron and figure out how many grams of iron 3 oxide that is. So again, I start with my given, which is my 12 grams of iron. So my only way to change from one substance to another is my mole ratio. So I have to get iron into moles. So I'm looking for some tool that has moles and grams in it, and it's molar mass. So grams of iron will be on the top or bottom to cross out, and moles of iron will be on the top. This is my tool, molar mass. Again, I like to come back and fill in all my numbers at the end so that I can think through my units. So moles of iron are on the top. I don't want moles of iron, so I have to put moles of iron on the bottom so they'll cross out. Now, my only way to change from one substance to another is my mole ratio, so this is going to be my mole ratio. And I want moles of the rust, Fe2O3. Now I have moles of rust, but I don't want moles of rust. I want grams of rust. So again, do I have a tool that has grams and moles in it? Yeah, it's molar mass again. So I'm going to use molar mass. Again, a different molar mass this time, but molar mass. So moles of rust are in the numerator, so they have to be in the denominator. And I'm going to have grams of my rust on the top. So now I'm left with the units that I want, right? I was looking for grams of iron 3 oxide, and that's what I have. So I know that I'm done setting this up. Now, my numbers. Now, my molar mass, again, when I look at my toolkit, right, the number in front of moles is 1, and the number that goes in front of grams comes from my periodic table. So moles is 1. I look at my periodic table, and I want to use 4 significant figures because this has 4 significant figures. So I want to make sure all my numbers I use for my molar mass have 4 significant figures. Iron is 55.845, so I'm going to use 55.85. Now, in my mole ratio, my numbers come from my coefficients of my balanced equation. So on iron 3 oxide, my coefficient is 2, and on iron, my coefficient is 4. This is molar mass again, so my number in front of moles is 1. To get my molar mass, I'm going to add up my iron and oxygen. So I have 2 irons, so 2 times 55.845 plus 3 times 15.999. And I'm going to use forcing figs. My calculator gave me 159.687. So I'm going to call that 159.7. So now I multiply my numbers that are in the numerator or on top. I divide my numbers in the denominator. So I'm going to do 12 times 2 times 159.7. I'm going to take that answer. I'm going to use parentheses because I need to divide by both these numbers. And I'm going to put parentheses 55.85 times 4, close my parentheses, and hit my equals. And my calculator gives me a big long decimal number, but I want 4 significant figures. So my calculator gives me 17.156666965. So with 4 significant figures, it's 17.16 grams of rust. So again, this is exactly what I expect to see on a homework assignment or a test or quiz. Normally, these problems are going to be worth 5 points. 1 point for your answer, 1 point for your units, 1 point for having significant figures correct, and then 2 points for having your work. It means that if you don't show me any work and all you have are answers, you're going to lose 2 points out of 5 points on every single problem. You have to show me your work. So that was the first problem we were going to do. And again, the one thing that is nice about these problems is that they're very consistent in that you need molar masses, mole ratios, and then a molar mass again. That's very consistent with these mass problems. So the second part of this example was what volume of oxygen is needed to react with 12 grams of iron at STP. So again, we have our equation, and I'm just going to recopy our equation because we already wrote it and balanced it once, right? So we don't need to do that again. This problem is saying I still have my 12, I will write it underneath. I still have my 12 grams of iron, but this time I want to know what volume of oxygen. So volume I'm going to measure in liters, and it does tell me that I'm at STP. So, again, I'm going to start with my given. So I'm going to start with my 12 grams of iron. And I'm going from one substance to another, iron to oxygen, so I know I have to get to moles. So I'm looking at my toolkit and I'm wondering, do I have a unit or a tool that has grams in it and moles in it? And I do, right? The name of that tool is molar mass. So now I'm in moles of iron, which have to go on the bottom. This time I want to convert that to moles of oxygen, so that's going to go on the top. Now, I don't want moles of oxygen though, I want liters of oxygen. So the question is, do I have a tool on my toolkit that has moles and liters in it? Yeah. Right, this tool was our mole ratio. Moles of oxygen have to go on the bottom, so they'll cross out. And liters of oxygen is going to go on the top. This is my molar volume tool. Now, again, I like to come back. I like to do all my units first and then do my numbers. If you like to do your numbers as you go, that's fine. So I look at my toolkit and I'm looking at molar mass, and the unit that goes in front of moles is always 1. In front of grams, it's a number for my periodic table. I want to use 4 significant figures, so I'm going to use the 55.85 again. That's my molar mass of iron. My mole ratio, I look at my toolkit. My toolkit says my mole ratio, my numbers come from my coefficients. So my coefficient on oxygen is 3, so I put a 3 in front of moles of oxygen. My coefficient on iron is 4, so I put a 4 in front of moles of iron. Molar volume, again, I look at my chemistry toolkit. On my chemistry toolkit, the unit in front, or the number in front of moles is 1, and in front of liters is 22.5. 5.4. So now I'm ready to do this mathematically on my calculator. I'm going to take 12, multiply it by 3, multiply it by 22.4 because those are all in the numerator. I'm going to take that answer and I'm going to divide it by, and I'm going to have to use parentheses because I have multiple numbers here. I'm going to divide it by 55.85 times 4 inside parentheses. I want 4 significant figures. My calculator gives me 3.609668756, but I need 4 significant figures because 12.00 has 4 significant figures. So that would be 3.610 liters of oxygen. Again, a problem like this would be worth 5 points. 1 point for your answer, 1 point for units, 1 point for significant figures, 2 points for your work. So that's where we're going to stop for today. Your homework assignment is on page 243 to do C, D, F, and G, showing all your work. So again, you need to show all your work. And again, this is not work you can type. So do not type this. You're going to handwrite it out on a piece of paper, nice and neat, showing all your work. Like the examples we did today, like the examples we did the other day when we talked about dimensional analysis, like we did back in Chapter 7 when we did these problems the first time. You're going to show all your work. You're going to scan it with the Adobe Scan app, or you're going to take a picture of it and turn that in. Have a great day. I'll talk to you tomorrow.